Hi there again. We're going to talk about covalent bonding again. This is an intense little section, so we're going to start off knowing that ozone is in the atmosphere, and it's a covalently bonded gas. And so oxygens join together, and they form something with 3 oxygen atoms in it. Compared to, I was telling you, oxygen likes to be diatomic. So let's move on. So what happens? How are we going to do this electron sharing for covalent bonds? Let's look at it. We're almost always going to follow the octet rule, where the covalent bonds makes the atom feel like it's got a full outer shell. And we're going to use electron dots like we did with ionic things. So for example, hydrogen is one of those diatomic molecules. It likes to be in 2s. Hydrogen has 1 dot because it's in group 1. And it doesn't feel complete like this, but if it could share these 2 electrons, it would feel like it has a full outer shell, because remember, hydrogen's in period 1, and it wants to be like helium, which has 2 electrons. So if these 2 share, it feels like they're sharing, it has 2 electrons. Each hydrogen feels like it has 2 electrons, so it feels happy that way. So every atom in these covalent things is trying to make an octet, or in the example of hydrogen, a duet, because remember this is a small shell. So we're going to use dots and dashes to show covalent bonding. And for example, fluorine's another diatomic. It likes to be in 2s because each fluorine has 7 electrons. It doesn't feel like it's full, and it's not stable that way. So if it shares these 2 right here, if 2 fluorines share these 2 last p electrons, it's going to feel stable. It's going to feel like it has everything filled up, and it's going to feel like the octet is filled up. So fluorine is another diatomic molecule. We need to know that fluorine, hydrogen, oxygen like to be diatomic for this reason. So sometimes we have electrons that are not shared, and that's called an unshared pair of electrons. They're all by themselves, they're not bonding. That's called a lone pair, or unshared pair, or non-bonding pair. So that's just a definition. So for example, these 2 electrons right here is a lone pair, unshared pair of electrons. When this happens, see, oxygen has 2 holes to fill to make it feel complete. So if it bonds with 2 hydrogens, those 2 holes will be filled up by the hydrogens, and it will feel complete. The oxygen will feel like it has 8 around it. Each hydrogen will feel like it has 2 around it, so it's happy that way. So this is all going to share right here, and everything in this molecule is stable and happy now because it's got a full octet or duet. So that's H2O. Ammonia, the same thing. We've got 3 holes for nitrogen. 3 hydrogens will fill those holes. And we have 1 unshared pair of electrons right there. So this is sharing, and then everybody feels happy and stable. Methane has 4 holes, so it's going to need 4 hydrogens to make that happen. So here's methane. Well, everybody is sharing and feeling happy with that situation. So they're very stable. But this methane has no unshared pairs. Everything is being bonded. So let's try hydrogen chloride. Hydrogen has 1 electron, chlorine has 7. So if this electron is shared here, then everybody feels happy. Okay? This has a duet. This has an octet. So there's some examples you can try on your own and check yourself on Google. And then sometimes those things that I was showing you here are single bonds. When 2 electrons overlap each other and share, that's a single bond. But we can have double and triple bonds as well if it makes everybody stable and happy that way. So we're doing that so that we have that full outer shell, that octet filled. So let's look at a double bond. When 4 electrons are shared, that's a double bond, and when 6 electrons are shared, that's a triple bond. So for example, oxygen, they both have 2 holes to fill, but if they make this double bond, then everybody is going to feel like this outer shell is filled up because they're sharing in a particular way to make a double bond. So I'll show you how to do that later, but this is showing you that we can have double bonds and it makes the octet filled up. These are the ones I need you to memorize. These are called the diatomics. So make some note cards for this so that you remember that we have diatomics, and these are other things to memorize. So I've asked you to memorize the ions, 1, and then diatomics would be really helpful for you. So please put those down for something to memorize. CO2 is, is in carbonated beverages. You're breathing it out right now when you're listening. And it's got 2 double bonds in it to make this sharing happen right here. The S's and P's are overlapping. And then it makes everybody feel complete. Each one now feels like it has 8 electrons around it. This has 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 8. And this oxygen has 8. So by doing double bonding, we can have that octet work out. Let me move on from this. It's just showing another double bond. And sometimes we have to move electrons to another place to get everything to be balanced out. I'm going to move on from here, but I also want to talk to you guys about polyatomics. These are the ones I'm wanting you to memorize. And so polyatomic is covalently bonded together, but the overall molecule has a charge to it. So ammonium is the only one with a positive polyatomic that we need to memorize. And it's good for fertilizing plants. These are the ones sorry. Let me move on to that. That's not what we need. Here's another polyatomic that we'll use a lot in this class. It's called hydronium, and this is the formula for it. And when this happens, water adds a hydrogen plus ion to it, and it turns into hydronium. So this is another one we need to memorize. Hydronium, H3O plus, and it's got covalent bonding going on here, here, and here. It's got a lone pair here, but this overall charge, that's why we put brackets here. This overall charge of this polyatomic is a positive 1 charge. So we're saying that here, we're saying that here, we're saying that here, just in different ways. So it's called hydronium. Very important. We're going to talk about it when we get to pH. And then these the covalent bonds have energy, so usually it takes energy to break that sharing of electrons, and that's called the bond dissociation energy. So how much strength does it need? How much energy is released when that bond, or how much energy do you need to put in to break that bond, and how much energy do you get out when it's broken apart? That's called the bond dissociation energy. So large bond dissociation energy corresponds to a strong covalent bond. So the tighter these are together, the happier that you have bonding going on, the more energy is involved in it. So let's look at the something called resonance. So this is a little bit more complex. We'll talk about more in the future, but let's talk about it now for just as an overview. We talked about ozone at the beginning. That's that bad chemical. It's bad to breathe, but it's in our ozone layer and it protects us against UV rays. So the bonding is actually hard to show in these Lewis dot structures. So it's actually a mixture of a few different drawings, and physically we can't really show it in one drawing. So it's called a resonance structure. So what happens is sometimes the electrons want to move from one place to another. And really, if we could show the cloud of electrons is actually equally shared between these 3 atoms of oxygen, and we can't show it with a Lewis dot structure. Lewis dot structures are limited in that way. It's really the electron cloud is smearing itself equally across the 3 oxygens. And so that's a resonance structure. So if you can draw a Lewis structure and you can show it in multiple ways, there's probably a resonance going on, and the electron cloud is sharing equally over the entire molecule. So that's resonance, and I'll show you that later, but this is an introduction to resonance. There's some exceptions to that octet rule. Remember, everybody feels like they need to have 8 electrons around them except for helium and hydrogen. They have the duet rule, excuse me, because they have a smaller shell. They just have that 1s. Sometimes elements in odd numbers like group 5 will do this weird thing where they won't follow the octet. So like boron does this, some other things do that. And sometimes you can have you can have 2 different electron dot structures, like we were just saying. And that was resonance. So let's talk about this. Sometimes like elements in odd number groups can expand their valence. So this is having actually 2, 4, 6, 8, 10 electrons around phosphorus. So it can expand its octet from the usual having 4 bonded things to it. It can expand to wanting to have 10 things around it. So some things do not, here's 6. So some elements are unique and they can get more than the 8 electrons around them. So those are exceptions to the octet rule. So let's start a quiz. Okay. When we have covalent bonding, atoms are attaining the configuration of noble gases by, how are they doing that in covalent bonding? So they're sharing. So like I said, they're sharing their clouds so that they feel better and more stable that way. Electron dot diagrams are superior to molecular formulas in that what do they show? They show which electrons are shared, so they're a little bit better than just showing a formula like H2O. A dot diagram really shows what's happening in a much better level. Last one, which of these would have a bond form when atoms share 3 pairs of electrons? So this one you have to draw out. So you might want to try this out, see if you can do a triple bond on this. And this is what you would find if you try all these 4 examples. So I hope you learned a little bit about covalent bonding. This is an intense section too. We need to talk about it more, but this will give you an introduction. It's good talking to you guys. I'll talk to you soon. Bye-bye.